after lunch. I got to keep it entertaining. We're good? Set? Yeah. All right. Cool. Anyway, thank you. Welcome to start of the afternoon session today. I'm going to be giving you a talk on basically an introduction or a kind of a rush job on scanning electron microscopy and focused ion beam. Hi. I'm Matt once again. Just would like to say thank you to my other colleagues in the electron microscopy core, Hongwei, Jim, CQ, and Vasek. Who've all given me a lot of good advice and valuable contributions to this talk. So it's kind of a collaboration from all of us. So a general outline of kind of what you're going to see in this talk is an introduction to the scanning electron microscope, the focused ion beam. What is it? Then we're going to transition to each one. How does it work? We're going to break down the individual components. And then we're going to go to the fun part. What can it do for you? So by the time that we're done with this talk, I'm going to give you a general idea of what you can expect as the operator. So by the time that you are sitting in the command chair here, all right, you have an idea of what's going to happen on the scope. So moving along, I'm going to read off the slide real quick for just one sentence here. So an SEM, okay, is an instrument for observing and analyzing the surface microstructure of a bulk sample using a finely focused probe of electrons. So typically, a SEM can achieve 1 to 4 nanometer resolution, depending on the instrument type and some of the components. We'll break a little bit of that down later. The primary applications for SEM, typically topography and morphology of a sample, but compositional analysis is a major component of a SEM. We can also do some crystallography and some optical and electronic property characterization, and there are many, many more. There's tons of techniques. We'll try to focus on the major ones during this talk. So before we get into kind of the nitty-gritty, we're going to go back to sort of an overall definition. Resolution. So you've heard that maybe a couple times today, and I just want to take just a few seconds and say, what is really the definition of resolution as we term it in an imaging system? Okay. So what we want to be able to do is tell the difference between 2 points, okay, that are sitting right next to each other. All right. So this is the difference between 2 things sitting right next to each other versus now 2 things that are so close that we can't resolve them versus 2 points versus 1 just larger particle. All right. And this is what we call an Airy function or representation of the Airy function. It comes from diffraction effects. All right, and if we can resolve these 2 points, then it's resolvable. So when I say 1 to 4 nanometer resolution, you can tell the difference between 2 things that are sitting right next to each other that are of that size scale. It does not mean that those 2 things are going to be perfectly sharply absolved and beautiful. All right, so some numbers, just to throw out. Some resolution limits based on just diffraction. So I'm sure you've seen this equation before. And just throwing out some numbers here, and it's why do we want to do this compared to the main technique, optical microscopy? Optical is the one thing you're probably all very familiar with, right? You've used them all in secondary education, high school, even. The main advantage that we're getting here compared to light, we're using electrons, is that light, your wavelength around 400 nanometers or so is your imaging wavelength, as compared to an electron. We're talking, the wavelength there is down to very, very, very small. All right. And actually, I think I got might have the wrong number on there, but that's okay. So the other difference here is the numerical aperture. Light's around 1. Electrons a little bit different due to the convergence angle of the beam. But just the hard numbers, practical resolution for light microscopy, you're sitting around about 200 nanometers of where you can resolve. And that's going to depend on the instrument, some of the optics. For an electron beam, you're looking around 0.3 nanometers. This is the diffraction limit of the system. So practical magnifications of those 2 things, around 1,000, 2,000 for light, about 500,000 for an electron microscope. All right, now, once again, this is the best possible resolution. Things will just become worse as we go through the system. So we're going to have other lenses. These are going to reduce our resolution. Just a quick comparison, so optical versus an SEM-based image. There's 2 things you're going to pick out of this. One, obviously, the resolution is much better for the SEM image versus the optical. The second one, which sometimes we don't keep in mind, is what's called the depth of field. And that's how much Z, okay, or how much depth of the image is in focus at any given point. So we can see here in the optical scope, the top part of this sample, okay, is in focus, and the bottom part's pretty fuzzy. And now in the electron microscope, virtually all of this is in focus at any given point. And this has to do with the convergence angle of the beam and, of course, the resolution of the system. So the major components of a SEM in a quick breakdown. First thing, we have a vacuum system. We'll talk about that a little bit later in terms of sources. Sources require a vacuum. Okay, your electrons also require a vacuum. So we have a source, okay, which is going to produce your electrons. Usually sits on the top of the column. And then we have a set of optics. So once we have our electrons, how do we focus them? How do we make sure we get rid of the aberrations that are associated with the lenses? All right, that will all be part of the optics. Then we move on to a scanning system and a set of detectors that once your electrons are hitting your sample, how do we see stuff? So moving to electron sources. This is going to be a quick general breakdown of how an electron source works. It's going to contain a filament or a needle, all right, a set of extraction electrodes or a rough electrostatic lens, and then you're going to have an anode plate which will set your acceleration voltage. Will accelerate the electrons down the column. So the source is going to contain these three major components. What it does is it produces electrons, it roughly shapes the beam, okay, and then sets, once again, your acceleration voltage. There's two types of sources. Thermionic sources that use heat to produce electrons, all right, and then there are field-emitting sources that use an electric field to produce the electrons. Each source has advantages and disadvantages. And now as we move on, the sources. First one, thermionic sources, which is effectively the fancy light bulb of the electron source world. Basically what it comprises of is a tungsten filament, okay, for tungsten, and we have some lab 6 crystals as well. You pass a current through this, you produce heat, all right, and the idea here is to take electrons from the top of the conduction band, heat them up so much that they overcome the work function of the material, and they escape into the vacuum level. So the question now is, how hot is hot? All right, for tungsten, you're talking 2700 Kelvin. For lab 6, you're around 1800 Kelvin. Of course, if air hits these, okay, while it's at that high temperature, they explode. And that's not fun for anyone, hence the reason for the vacuum system. So yeah, came back to it, so don't worry about it. We'll all get there. All right, now, major advantages of this type of source. Very high probe currents are obtainable, very stable currents, okay, good for analysis. And you don't need as complex as a vacuum system, okay. Mostly the reason being there is the very short lifetime, okay, of these filaments. And they tend to be a little bit lower resolution too because they're just larger. All right, these are kind of sacrificial filaments that we use in training scopes or other scopes that need less stringent vacuum requirements. Now, the sources that are more resolution-oriented are field-emitting sources. These sources are a little bit different. They still use tungsten, but they're going to come to a sharp, tapered tip, okay, a few nanometers in curvature. And instead of using heat to produce the electrons, we now keep them cold, okay, and we use an electric field to actually strip electrons, okay, off of the very tip of the emitter. So you have a first anode, okay, which is going to strip electrons off of the source, and then you have a second anode that's going to accelerate those electrons down into the column. All right, so instead of going up and over the thermal barrier, you now go through a new barrier that the electrons can quantum mechanically tunnel into the vacuum level. All right, so that's the basis of a field emitter, and the main point of there is cold. All right. Major advantages, very high resolution. I put best with a question mark because the next source and this one kind of compete a little bit for best resolution. Has very good lifetime. So these last a very long time compared to thermionic sources, years. Disadvantages, they don't have very good probe currents. Okay? They tend to have fairly poor stability, and they need to be flashed periodically. Because the gun is cold, all right, any molecules that are in the gun head, if they get attracted to it and they mess up kind of the tip shape a little bit, then you're going to get less emission. So occasionally you have to flash it, and that gets rid of all those molecules, and then your current will go back up. So over time you're imaging with this source, and your image gets darker, 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 and you say, hey, what's going on? Oh, I need to flash the tip, hit the button, and normally that takes care of it. And that's the other reason, ultra-high vacuum in the gun area. Need that. Finally, the last source, the Shocky source. This is your hybrid heating and electric field extraction source. It uses the same type of filament or needle as a field emitter, sharp tungsten tip, but it has this additional zirconium oxide coating right here, which lowers the overall work function of the surface. All right, so instead of going purely this way or purely this way, we now go over a little bit of a hump here. And we get kind of the best of both worlds between the sources. You have very high resolution, you have very good probe currents, long lifetime, good stability, still requires ultra-high vacuum in the gun area, and of course, since it's being heated, you now have a bit more of a finite lifetime. So maybe a couple years compared to just a pure cold FEG, that's going to be several years, at least. So that's sources. We've got our electrons, they're flying through space, that's great. What do we do with them? Okay. Lenses, all right? We need these to focus our electrons and get them down the column. So we're going to talk about the lenses and the aberrations that occur from these lenses. So the primary lens that we use is an electromagnet. All right? The reason being is that we can't have the same focusing optics that an optical microscope has. If we put a big milled piece of glass, the electrons will hit that and just scatter all over it, and there's be no point. So the electrons have to go through vacuum. All right. And what we use is a coiled set of wire, copper wire, around a soft iron pole piece, and we pass a current through those through that set of windings, and that's going to produce a magnetic field. So how we work with this magnetic field is that a very small slit, okay, is cut into this iron core, and that allows the magnetic field to leak out in a very controlled fashion into the center of the microscope. And by controlling the amount of current that we pass through the windings, that lets us control the magnetic field and hence the focusing action of the electrons. And so how this works is that we have a magnetic field, we have a charged particle, okay, that's moving through this magnetic field, and it's going to see a force based on the Lorentz equation, velocity cross the B field, the magnetic field. All right? And that's always going to give us a inward focusing action. The lenses. There are two primary lenses, okay, that we use in an electron microscope. The first one is the condenser lens. The condenser lens sets the spot size, okay, of the probe. And how it works is that up here we have our electron source, our anode, condenser lens right below it. Based on the convergence, okay, of the condenser lens, we set the spot size. So when the condenser lens is in a low convergence type point, it's in a weak lensing condition, all right, all the beam is going to pass through this limiting aperture. If we now, okay, change the convergence point of the beam, some part of that beam, okay, is going to be cut by the limiting aperture, and that gives us less current and a smaller spot size. So overall, if we have a low convergence, we get more beam is accepted through this limiting aperture. This gives you more current, but your probe size is larger, so you have less resolution. Good takeaway there. At a high convergence, we have less beam accepted through the aperture. This gives us less current, but it gives us a higher resolution. So if you are an SEM operator or a budding SEM operator, this is one thing to keep in mind, is that based on what current you set in the instrument, this will affect the performance, okay, the imaging quality that you get. The second major lens that we have is called the objective lens. All right? That sits right below the limiting aperture here. And what the objective lens does is it sets, very similar to an optical scope, the focus. So based on changing the lens strength, we can change the point at which the system focuses. So we have in this one here, this lensing condition sets us exactly the focal point of the sample. Okay? If we do this too strongly, we have an overfocus condition. If we go now to a weak lensing condition, we have an underfocused situation. So obviously these two, we're out of focus. In this one, we are at focus. This is commonly called the working distance, the distance between the objective lens and your sample or the stage. This is a good way to read out kind of where your sample is in space, and you'll typically find this on most SEMs. So we have these lenses. Ideally, if we have a point source, it's going through a lens. We want that point focused back to a point. But life doesn't exactly work the way that we want to, and that's why we can't have nice things. So the actual lens here, okay, is going to focus us to more of a disk. Right? It's what we call a disk of confusion. All right? And several effects are going to contribute to the size of this disk. And these are these limiting parameters, which are our aberrations. Spherical, chromatic, aperture diffraction, and astigmatism. Astigmatism is in red here because that's something that you as the operator can correct all the time on a SEM. So I'm going to step through kind of the aberrations fairly quickly. The first one is chromatic. And what happens with chromatic is that, say for instance, we have 2 electrons. And these 2 electrons are going to pass between this path from P to B here and go through this lens. Now, if these 2 electrons have different incoming velocities or energy, they will be focused to 2 different points on the sample. So we have one ray that's going to pass where we want it to, and then we have another ray at different energy that will now pass to a different position. And this gives us our defocal disk. So where this comes into play is that if you're using a heated source, thermionic source, okay, or a shocky source, you have an energy spread that comes off that source. That energy spread will then translate into chromatic aberration in your system. This is particularly pertinent for a thermionic source, which has the worst spread. So what this means is that what we can do is, if we increase the electron energy, the acceleration voltage of the beam, we can decrease the effects of chromatic aberration, because the chromatic aberration spread, the energy spread of the electron, becomes less of the overall acceleration of that electron itself. So when you're working with a thermionic instrument, you typically want to operate at a higher acceleration voltage in order to mitigate your chromatic aberrations. All right, so that's the one thing you got to keep in mind when you're working with a thermionic source. The major limitations, okay, for your other source types are typically these: spherical aberration and aperture diffraction, and they kind of go hand in hand. What spherical aberration is that electromagnetic lenses are not uniform throughout the radius of the column. All right? Focusing action becomes stronger towards the outside, so ray paths that are passing, for instance, from P to B here tend to get over-focused, whereas ray paths, for instance, P to A, which are closer to the optic axis, now get focused approximately where we want them to be. Where this comes from is, actually, sorry, I'm getting a little ahead of myself there. But basically the idea is that the magnetic field is not uniform, stronger on the outside, weaker towards the center. Off-axis rays tend to be over-focused. The solution to this is just cut them off. Just get rid of them. Why do we need these? They're reducing our resolution. So now we come to aperture diffraction. If we put in a limiting aperture and say, let's cut down all the high-angle rays, well, why can't we just make it as small as possible? So an electron still acts the same way as light, okay? The Airy function, Rayleigh criteria all come into play here. All right, diffraction effects will increase with a smaller aperture. So if we make it smaller and smaller and smaller, now your aperture diffraction is going to increase significantly. So typically optimum aperture sizes are determined by the manufacturer. They're not going to give you an aperture that's going to completely destroy your imaging capability, but generally speaking, as you make that aperture smaller, you're going to lose some current. Okay, but you'll mitigate the effects of spherical aberration. So you'll hear a little bit more about this in the TEM talk, because this is a very important effect in how we deal with spherical aberration in those systems, and particularly what methods we use to correct those. So the last major aberration that we have, okay, is called astigmatism. And this is the one that you guys as operators can correct on a daily basis. So astigmatism comes from if we have the same origination point of your ray, and it's passing from, say, P to the y-axis, P to the x-axis, these rays are focused to different points. So this ray particularly is over-focused, and this ray is under-focused. And what this creates in the image plane is an elliptically shaped probe. And what we'll see in the SEM when you have this condition is that your image is going to look stretched. Okay, so we see here, this image looks like it's stretched in this direction, and then you see it's kind of sharp over on this side. If we go through the focal condition, we can then see that now the image here is stretched in this direction and now kind of sharp on this side. Now where astigmatism comes from is that we have slight imperfections in the manufacturing of the pole piece, in the copper windings. You can have stray magnetic fields. The operator may not be very good sometimes. That tends to happen. But we can do some things to correct this. All right, so we have a set of deflectors in the system that are designed specifically to counteract astigmatism. And these deflectors, instead of being wound kind of this way, all right, are wound in this direction. All right, and what happens here is that now these electromagnetic lenses are pushing and pulling. They're kind of stretching the beam in order to get rid of that elliptical probe. So what happens here is we have the basis of this quadrupole. Okay, we put a couple of these together, we get the modern octopole stigmator. All right, and through a combination of working with this, we apply our stigmators. And then what happens here was we change our ray paths So we turn our elliptical probe into a circular probe, and we can eliminate the stretching in the image. So the transition here is from a stretched beam, and now we have an image where everything is pretty uniform, but still fuzzy, right? So this is what you're looking for as the operator. If you correct your astigmatism to the point where everything is uniformly fuzzy, you're good. Next thing, change the focus of the objective lens, and now make that circle as small as possible, and you've got a nice focused image that you'll then take it, you'll put it on the cover of Nature, and you'll make everyone famous. Okay, so we got our electrons. They've gone through our lenses. We're focused to a nice probe. We've gotten rid of as many aberrations as we can on the system. We're keeping some of those things in mind depending on our source. How do we form an image? What does that do? So say we have our detector. Okay, we've got our sample, and our sample is kind of sliced into this grid, shall we say. Now as the beam is going to be scanned across with a set of deflection coils, okay, the interaction of the beam plus the sample will produce some emission. Okay, you have electrons, you have light that could come off, and what happens here? So as the beam scans across this first pixel, all right, we get 5 counts, and that's a bright pixel. Then if it scans across the next section, okay, picks up 2 counts, and that gives us a dark pixel. All right, so it's effectively a proportional counter. If you've got a lot of counts, you're going to get a bright pixel. If you've got fewer counts, you're going to get a dark pixel. Now, I don't want to give you the impression that the beam is sort of just scanning one little section at a time. The beam is constantly going. Scanning electron microscope, beam is constantly rastering across the sample. Looks more like this. If we have our happy smiley face on the surface here, we got our beam, we got our monitor, and the beam's going to start scanning, and it's going to scan lines, and eventually there's our little happy smiley face. There she is. Very good. And the beam will scan, 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 and this is what you start seeing on the screen. And then as it finishes, what will happen is the beam will come back, and will start scanning again. So it flies back to its initial point, it'll start scanning, and then go over and over and over and over again. That's your live imaging mode in the SEM. So as that's kind of wrapping up, the magnification in a SEM, it's kind of an interesting point, is defined by the screen size, so your CRT, your computer monitor, whatever it may be, okay, versus the raster size of the beam. So if the raster size is large, okay, your magnification is lower. If the raster size is, say, very small, like let's say we scanned across just the eye right here, your magnification is larger. So you're not particularly changing anything in the optics to make the magnification different. What you're changing, okay, is the raster scan size. That will dictate your magnification because your screen is approximately fixed. Now, once we now have the system scanning, okay, electron-matter interactions and the detectors, okay, that will be looking at these interactions. So when the primary beam comes in and hits the sample surface, there are a wide variety of particles, okay, and quanta that will be emitted from the sample. And particularly what we're interested in is other electrons that are emitted from the sample and characteristic X-rays. Now, of course, we have some detectors that can deal with light, that can deal with certain scattering effects, and we'll kind of talk about those as we go through. But these are the ones that we really care about: secondary electrons, backscattered electrons, and characteristic X-rays. So what are these things? 2 ones: secondary electrons and backscatter. A secondary electron is, by definition, a low-energy electron, okay, that's emitted from the interaction of the primary beam with typically the valence shell of the target atom that it hits. And that will, you have your incident electron comes in, it's going to interact here, it will eject an electron, okay, and now that electron is free to go and do things. As opposed to, say, a backscatter electron is a primary electron that comes in, it interacts, with your target atom here, okay, and then it gets scattered over large angles. These 2 things are going to carry different forms of information, and we'll get to that in a few slides. Before we do, just want to talk about characteristic X-ray generation in a SEM. You have 2 types of X-rays that you can get. You can get a continuum X-ray, sometimes called a Bremsstrahlung or white radiation. And what this is that you have an incident electron, it comes in, it interacts with your atom here. And then as an effect of that interaction, that electron will be slowed down, it will be braked, and due to the conservation of energy, that electron will give off an X-ray to maintain its momentum. All right, now on the other hand, okay, if you have an incident electron comes in, it knocks out a core shell electron, An electron from a higher level orbital will jump down to take its spot, and when it jumps down, it's going to emit an X-ray, and that is characteristic to the atom from which it came from. So this is how we figure out what do we have inside of our sample. So the spectrum looks a little bit like this. We have our background, which is the blue continuum X-rays, and then we have these sharp peaks, which are the red characteristic X-rays, which actually identify the elements that we're interested in. So these are the major things that are going to come off the sample that we're going to use, for our detectors. So the next part here is the interaction volume of a primary electron. So what's happening is that we have a primary beam, it comes in and it hits the sample, and what does it do? Does it just stop? Not really the case. It's got a lot of kinetic energy. It's going to bounce around within some interaction volume here, and it will eject electrons, X-rays, but specifically we care about where they come from. First one, for a secondary electron, their energy being very, very low, their range when they're created is only about a few nanometers. So let's say we have a primary electron that comes in, it hits the surface here, and starts rattling around the interaction volume. If a secondary electron is generated around this point, it can only move a couple nanometers before it's going to be reabsorbed by the sample, in which case that secondary is not getting out. The only secondaries that are getting out of the sample are the ones that are emitted from the near surface region. Within the first couple nanometers of most materials, those electrons that come out. So a secondary electron is surface topography oriented. That's what you're going to get your surface topography information out of as an SE-based detector. Now a backscatter electron, on the other hand, kind of same principle. The primary comes in, it rattles around, gets scattered over a high angle, and now flies back out essentially from whence it came. All right, this carries a little bit of different information. The scattering is based on the material, the average Z of that material. And this lets us do some basic Z separation. And finally, X-rays. X-rays are going to come from the total complete volume, and this is all elemental-based information. So a quick example of an interaction volume here. This is 20 keV electrons in PMMA, and this shows you that this teardrop shape is not just something that I like to draw. It is real, and it can be simulated with Monte Carlo or statistical software. So as an example of just what you see in the microscope from a beam energy perspective, why do you set one energy versus another? And it depends on the interaction volume that we just talked with. Let's take, for instance, this sample, which has gold flakes, and then there's some gold particles sitting underneath of those flakes. At a high acceleration voltage, around 15 keV, what you see here under this flake, you can clearly tell that there's some particles sitting underneath of it. The mechanisms that you're seeing here, from an image formation standpoint, is that you're getting secondary electrons from the flake, you're getting some backscatter electrons that are coming from underneath of that flake. So you're seeing a lot of depth-based information at a higher acceleration voltage. Now as we start stepping down that acceleration voltage, the amount of material that you see underneath the flake starts becoming smaller and smaller and smaller, to the point now at 1 keV, you're getting essentially all surface-based information because your interaction volume is confined to the near surface. So you have to be a little careful as an operator to know kind of what you're seeing and whether you have kind of a defect in your sample, or if what you're really seeing is kind of on your surface. Moving on to the detectors, and we're going to start getting into the fun pictures, I promise. Okay. An SE-based detector, which is commonly called an Everhart-Thornley detector, it uses a biased grid, typically a couple hundred volts positive, which are used specifically to attract the low energy secondary electrons. All right? So as we see in this schematic here, the low energy secondaries are attracted to this biased grid. Okay? It will collect some backscatter electrons just from the solid angle. So whenever you're using an SE detector, you're getting all the SEs, plus you get a little bit of backscatter information. Those electrons hit a scintillator, which transforms it into light, hits a photomultiplier tube, and that gets read out through your preamplifier. That's the basis of an Everhart-Thornley detector. Now, the contrast mechanism for the secondary electron generation itself is really based on the topography of the surface. So as the surface curvature increases, okay, the effective tilt of the sample towards the beam, you get more secondary electrons generated. So based on this chart here, the number of SEs is going to increase as the tilting increases. And it's based on effectively an inverse cosine. So what happens here, if you have spheres, okay, on your surface, what you see is that right around the edges where the curvature is the highest, those are bright, okay, towards the top of your sphere, where now your surface is leveled out, that's going to give you a more duller contrast, okay, or a darker type contrast. Some examples, okay, of SE-based imaging. Dendritic gold here, we can see some nice surface microstructure. And then just one kind of resolution-based image. Note the scale bar here, 10 nanometers, about that. And we can see these small, sputtered AU PD particles on magnetic tape. So the vast majority of these particles are sub 10 nanometers. All right, typically speaking, you'll be able to resolve things around the 2-3 nanometer range in an SEM with an SE detector. Some other examples of things you're typically going to be doing in a SEM. Okay, you see things, you measure things. All right, so let's say, for instance, we got some zinc oxide particles on your surface, and we can measure, all the little facets. Okay, what size these particles are. For instance, here, this was some work that I did a while ago, where we were cutting out the coating on some of these carbon nanotubes, and we were trying to measure, well, how big's the tube, how big's the coating. Whatever you see on the screen, typically you're going to be able to measure it right on the screen and get some instant feedback on what your particle sizes are, or what your film sizes are. And lastly, you can do things, observe your world, okay? Be a little artistic, take a fun image every once in a while, okay? This was a mixture of silver, some surfactants, okay? This was a carbon nanotube bundle image I took down at Oak Ridge. It's fun. You get to see all the things that you never, ever get to see on the nanoscale. And that's the major kind of sticking point of SEM. If I were to say anything else, you get to see a lot of cool stuff. So let's move on to backscatter detectors. Okay? How a backscatter detector works is that you get increased scattering of your primary beam with the sample Z. All right, so if we look at this plot here, the backscatter coefficient will increase, not linearly, but always increase as a function of the atomic number. So typically a backscatter detector is going to sit directly under the pole piece. So that's this piece right here. Here's your sample. Okay, the quadrants are right in here. And actually, this is the cage of the Everhart Thornley off to the side there. I forgot that was in there. So with this backscatter detector, you can do things like phase separate, okay, or Z separate in this case. Two examples. One, a chip here. In this SE image, you see very little contrast. It's a flat, smooth surface with some buried lines. Under the backscatter, what it picks out is the lines, okay, the interconnects that are in there. So chip manufacturer uses quite a bit to show where your buried lines are, if things are connected, disconnected, etc. Another good example, okay, SE image on this side. This was a sample that a company gave me, and they wanted to know, well, I've got this material, does it have fillers in it? Does it have things that are kind of keeping the structure, making it stronger, making it more durable? And you really can't see these structures except for a surface and a bunch of cracks in it in the SE-based image. But as soon as we turn on the backscatter detector, now all of a sudden these filler particles light up like light bulbs. All right? The background is low Z. These fillers are very high Z-based materials. So I can tell exactly where the source of that is coming from, and then use things like EDS, which is the next detector we're going to talk about, to figure out what these particles are. So, good transition. X-ray detection and energy determination. How does this work? Generate an X-ray, okay, through the natural interaction of an electron with the sample. Okay, that X-ray is going to hit the detector, and when it does, it's going to, through inelastic collisions, generate a bunch of electron-hole pairs. And what happens here is that we apply a bias to this detector so that these electron-hole pairs can't recombine. All right, and they are going to be swept, okay, to the different electrodes of this detector, all right, and then they're going to be counted. So every electron hole pair that's generated is counted with the detector, and then these are all summed up based on the energy of a silicon electron hole pair, and that is reconstituted into one X-ray count from the X-ray source that it came from. And that's going to give you the individual peaks that are characteristic to that element. So things that we can typically do with an EDS system is we can do some point and shooting, we can do mapping. There's a lot of good stuff we can do with an EDS system. But just getting a little out of myself here, mostly this is a qualitative elemental analysis technique. Typically, beryllium and up is what we can look at. Sensitivity is around 0.1 weight%. Quantitative analysis is a little tricky with an EDS. Really requires standards, really requires a homogeneous, polished, well-prepared sample, and the vast majority of samples that you guys have are not that. And we typically don't have a standard that matches exactly what you're working with. Sometimes we do, sometimes we don't. So if you want to do quantitative analysis that requires a little bit more thought into your experiment, highly recommend talk to us and we can work on getting you quantitative analysis. We have point line mapping scans, which a good example of mapping is down here, where we can take an SE image, a backscatter image, and then we can separate out the individual contributions of the elements that comprise those images. So particularly, backscatter and the elemental analysis, okay, is very powerful because the backscatter shows you in your electron beam image kind of what it looks like, okay, and then we can overlap, you know, these individual elements on top of the picture itself, and you can have a very good representation of where the signal is coming from in your sample. That analysis, of course, is throughout the entire interaction volume, so you have to be a little bit careful about buried structures, okay, or heterogeneous structures. We have a resolution of about 130 EV. This is an industry standard. And this is important because it's going to come up next. So 130 EV, this is why we have some width in these lines. Now the complementary technique to this is called wavelength dispersive spectroscopy. And you want to use this when you just don't have enough resolution in your EDS. How it works is that your electron beam comes in, hits a sample, generates X-rays. They're going to fly up into this flat crystal here. And the crystal is used to separate out X-rays very specifically. And this is going to give us much more resolution than we had previously. So 130 for the EDS, about 5 EV, okay, for the WDS systems. What this does, okay, it highly minimizes element overlapping. So let's take, for instance, this spectrum down here. Okay, this is the red is the EDS, and then the blue is the WDS. So we can see within this one silicon peak. Now with the WDS, we can pick out a very small tungsten inclusion here. And we can have the individual peaks for tungsten, and we have our peak for silicon. On top of this, the detection limit for your WDS is a little bit better. And so those are your two main advantages. Okay? You've got less overlapping, okay, and you've got better sensitivity to the sample. So moving on to now crystallography. All right, these are some more specialized techniques in SEM. All right, first one's called electron backscatter diffraction. And what happens here is that if the beam hits your sample at a very high angle, okay, we can get these things called Kikuchi bands. And Kikuchi bands are formed by the scattering off of each individual plane of the surface. So you see here, one plane, the red line, okay, another plane, the yellow line, and the blue plane, blue line. And what we get is different patterns, okay, based on the orientation of your sample to the beam. Based on these patterns, we can now do some mapping and determine, you know, what orientation is coming from where on your sample. And so what EBSD typically looks like is something like this. You're going to get this type of pattern, all right? Software is designed nowadays that will automatically index these patterns for you with a high accuracy. And then we take this data, we apply it per pixel, and we can get things like orientation. Okay, we can see grain boundaries, and you can pick out the grain size, okay, of your sample. One thing I want to point out, okay, is this gives you the orientation, the microtexture of your sample. It's not exactly giving you phase, though. Okay, if you want phase, go talk to Morrow, XRD lab. Okay, he's going to love the plug. Right, he's going to love that XRD can do something more better than the SEM. So go talk to him. If you want phase, go talk to Morrow, XRD. Now the next one, cathodoluminescence. Okay, in the SEM. What you're having here is that the electron, when it interacts with your sample, is going to give off some light. Okay? We collect that light with a parabolic mirror, and it tends to look like this. So here's your objective lens. Okay? It's going to go right through this little slit, okay, on the mirror, hit your sample. All the light's going to reflect off of that mirror, and it's going to go to your spectrograph. Right? So we have a fairly large range, optical range. You get decent spatial resolution. The primary applications of this, semiconductor defect analysis, quantum wells, plasmons. So some examples, okay? Defects in gallium nitride. So we can see point defects, line defects here. And then another decent example is emission from gallium nitride pyramids. So we can isolate out the exact emission points from this type structure. So one thing I really haven't discussed is what do you need to do about samples? You're injecting charge, okay, into your system. You have a beam current, okay? When the beam hits the sample, you have a backscatter current, you have a secondary electron current, and you've got a specimen current. If you're using a conductor, all is well, all right? Everything will dynamically compensate and things are fine. But what happens when you're dealing with something like an insulator or something that's just really not very happy under the electron beam, all right? You have a little bit of an issue in terms of charging. When you have charge buildup, you start getting things like distortions or other effects in your SEM. So this is a very good example of charging, where you'll see it's sort of like evanescent waves, or you see really strong contrast. So see you have this really bright like banding structures. This is a classic example of charge buildup in a SEM. To the point that if you really charge your sample, the beam comes in, it looks like your sample goes, nope, not happening, and goes straight back up, to the point where you start imaging the top of your column. So if we look at this image, we can pick out all the little individual parts. Here's the pole piece. Here's the Eberhard-Thornley detector right there. I'm pretty sure that's the ion beam for the FIB, getting a little ahead of things. And I'm pretty sure that's the platinum needle. So yeah, this is always fun. You take a little bead, you charge it up, and then we do the reflection. And that lets you see what's going on the top of your chamber, and sometimes that's useful. So what can we do about this? You've got two main methods to deal with a charging sample. All right, the first one is, as we've seen this image before, sputter coat it. So we have a couple of sputter coaters, all right, downstairs. Typical ones, gold and palladium, or you have carbon coating. You put a very thin layer of either of these two things, and now your sample goes from charging and insulating to now conductive. And everything is fine. So as long as your coating does not exceed the things that you're looking for, so if you're trying to look at 5 nanometer pores, coating is probably not going to be the best way of going about it. But if you have larger features, okay, things like soils or sands, okay, coating is a really good way of dealing with your charging sample. The next way of going about it is, let's say you can't coat your sample. You can do something which is called E2 point matching, which is basically we match the beam voltage, okay, to the emission that you get from that particular voltage from the sample. Now, we have here 2 points, E1, E2. E1, the acceleration voltage, that's too low for most SEMs. All right, it's going to be sub 100 EV or so. Now, E2, on the other hand, typically is much more in the range of your SEM. So what happens here is that I've got a list of some common materials and the E2 point that you would want to match on your SEM. The idea here is that if you match this point exactly, your sample will emit just as many electrons as you insert into it. So your insulator becomes essentially a metal, effectively a metal. So the only downside to this is that if you're using a thermionic source, okay, this is right to the point where chromatic aberration totally takes over. So in a thermionic source, you do not want to E2 match at any point. But if you're working on a cold field emitter or a Schottky, good chance you can do this and not have to coat your precious sample that you want to use for other types of analysis, or if you just really don't feel like it. The last method is to use a variable pressure or an environmental SEM. So we talked about before, remember, you want a vacuum, okay, inside your SEM. That's true up to a point. So there's the major advantage or a major technological advance in the past probably 15, 20 years or so is the development of variable pressure or full ESEM-based systems. And what they do is they isolate the gun, and just in the chamber will introduce a gas, typically air or water. All right? And what happens here is the primary electrons will ionize this gas that you introduce. It will create charged particles. Those charged particles will dynamically compensate the charging that builds up on your surface. Hence, everything will once again image very similar to a metal. Okay? So this is good for samples that cannot be coated. Typically, a VP SEM is going to run around the 2 torr pressure. A couple examples here. These were taken in our 6060. So I found this handsome specimen sitting on a windowsill somewhere. Stuck him in the SEM. Fairly decent image here. I think he's a mosquito, but not sure. Anyway, not a big deal. Next one, this was a plant. Okay, this came off of a magnolia in my backyard. I find a little wacky stuff to throw into the SEMs. But these are small stoma, okay, on the back of the plant. And just once again, none of these are coated. Okay, they just go directly into the SEM. Turn on the variable pressure, put a little bit of gas into the chamber, start imaging, and everything images just the way you'd expect it to. Now, the next part of it is that you've got a VP SEM. We also have full, what's called environmental or E-SEMs. All right? The major advantage of an E-SEM is that they always will come with a cold or heating stage, not always, but typically. And they can operate at very high pressures. So 2 torr, less than 2 torr for a VP. For E-SEM, up to 20 torr inside of the chamber. What this allows us to do is create a 100% relative humidity condition, okay, inside of the chamber. So for things that are very hydration sensitive, okay, this is the scope for you. To the point that we can do things like image water inside of the microscope. So this is some work that I did as a postdoc, and we were trying to form water droplets and move them around and stuff inside the SEM and do some chemistry with them. So we formed these directly inside the SEM, not inject them or anything else. So what SEMs do we have at MRL? We have 4. Okay, the Joel 6060, which is I'm in charge of, is a thermionic source. Okay, roughly 10 nanometer resolution. Thermionic's not quite so good for the res. Really good for things like geological samples, chip imaging, powder soils, most geological type stuff. Very good currents for EDS, chemical analysis and mapping. Has a backscatter detector, has the low vacuum variable pressure mode. That's the major advantage of this instrument. The Hitachi 4700 is our other trainer system. Cold field emission source, very good resolution. Has an EDS detector and a backscatter detector. Good for particles and anything with really fine surface detail. This is the SEM of choice for that. We have 2 advanced SEMs in the center. The first one is the Joel 7000. Has a Shocky source, very good resolution. And this is our quantification or chemical SEM. It's got EDS, EBSD, CL, WDS, everything you got on this system. Now, as opposed to that, we have the Hitachi 4800. It's got none of that. This is our straight, you want the best resolution possible at the center. 4800 is the microscope for you. It still has several of the electron beam detectors, but doesn't have any of the chemical analysis based stuff. You can get to these SEMs once you spent some time on the 6060 or 4700, demonstrate that you are a very good user. That's not going to break our microscopes, and you get to use the fun ones. Now, where does SEM fit kind of in the realm of all the techniques that you've been hearing about today? I tend to think that SEM is is mostly just a versatile system. That's its main advantage. Gets you information quickly, doesn't need a lot of fuss for your sample prep. It's sort of your jack of all trades. So resolution, very good resolution over a wide magnification range, but in the ultimate aspect of resolution, not as good as the surface probe technique or the TEM, which is what's going to be coming up next. For element identification, it's really good for what is it, where is it on your sample, through EDS and WDS, but in terms of knowing exactly what the composition of your sample is, maybe not the best technique for it. It can tell you approximately what your composition is. You can do better with standards, okay? You tend to have a difficult time with low Z materials. You might be better off with a complementary technique like RBS, XPS, or Auger. Okay, those things might be better for you if you want better composition analysis. Surface orientation or texture can be done with EBSD, but once again, does not give phase. Go talk to Mauro. Mauro wants to talk to you about XRD and have everyone use XRD and have that be the only thing that we ever use in the center. So, all right. Now the fun part, the focused ion beam, my favorite. Think of the FIB like this. If you ever played pool, if you ever bowled, okay, you've got a projectile. You're going to fire that projectile at other poor things that are going to get knocked around. So you saw the Sims talk this morning by Tim, which was really nice. And he had those images where he's showing you the sputter of all the atoms that go flying all over the place. Same principle. So we're going to take an ion. We're going to accelerate it at our sample. Okay, take a focused beam here, and we're going to mill our sample and cut it to pieces. So we can use this as a cutting tool. We can use it as an imaging tool. How does it work? We have several components that are a little bit different from your typical SEM. Right? First of all, the source is different. It's called a liquid metal ion source. It looks like a Schottky source, okay, except that it has this reservoir of gallium on it. And what we do is we heat a little bit of this, the gallium wicks onto the tip, and then we use a set of lenses to extract the gallium from the sharp tip, okay, and then send that down the column. Now, instead of using an electromagnetic lens, we use an electrostatic lens for a FIB. The reason being is that since the ion is so massive, okay, the velocity doesn't really change as much with the acceleration voltage, so the V cross B term of the Lorentz force isn't going to do much for you. But the charge aspect of the particle moving through the magnetic field will do a lot for you. So regardless of the mass of the ion, okay, we can use an electrostatic lens, okay, to change the focus. This is just a good example of a typical electrostatic or Einzel type lens. Path comes in, we have some difference between these individual plates, and that will give us focusing action on the ion beam. All right, what does it look like inside the chamber, and kind of what's the orientation of the things that are pertinent here? So we notice that it gets kind of cluttered and crowded inside the chamber. We've got an electron column, okay, on our FIB and dual beam systems. We got a FIB column that's sitting at 52 degrees off axis. We've got injection needles, our specimen stage over here, and then a variety of detectors. So we got a lot of stuff kind of sitting around this sort of central point here. If we kind of simplify this a little bit more, if we look at a rough schematic of what's happening, our electron beam and our ion beam are designed to converge around a point so that regardless of what tilting we use on our sample, the point that you're looking at is not going to move in the tilt plane. Okay, and the reason why we want this is because we want the electron beam and the ion beam to look at the exact same point so we can do things to our sample. Now, why do you want to tilt? In this case, if you're using your ion beam to cut, if your sample is at 0 degrees, you're now cutting on an angle. Okay? If your sample is now tilted to the axis of the ion beam, you're now cutting perpendicularly into your sample. So this is good for things like cross sections. The last thing that the focused ion beam was designed to do is to deposit materials. Okay? This is called beam-induced deposition. Sometimes you can think of this as a localized CVD type process, where you have a gas injector, a needle. It's going to have a precursor gas, flows through that needle. All right, the ion beam is going to hit the surface, okay, where that gas is generated. It deposits or breaks down these molecules right in the vicinity here, and you get some part of the precursor that stays and some part of it that flies away into the vacuum system. So we can build things, we can mill things, a lot of stuff that it can do. This is just an example here of, here's our platinum needle, here's our surface. This is very close. So the distance between the needle and the substrate, 50 to 100 microns or so typically. So that's a lot of fun when someone smashes the sample into the needle. Don't really like that. Got to be very careful when using FIBs. So what can it do? It can build things, it can destroy things, and it can do that stuff on a variety of different length scales, okay? And it can do things very accurately. All right, so you see the larger ones here, around 3 micron, 4 micron scale bar, and then we have some of the smaller matched images right into about the 500 nanometer range. So each of these lines is sitting around 50 nanometers or so. I particularly like this one. That's a lot of fun. This was done on our Helios system. But really, if you're not playing with it, what do you really use a FIB for? Cutting through materials and seeing cross sections. So if you want to know the exact thickness of a deposited layer, okay, this is what FIB is good for. In the IC industry, if we're cutting through and we want to look at the chips, okay, look at individual layers, see if things have defects, if they're connected, disconnected. One of the major early applications of FIB was for the semiconductor and chip analysis. Another good example here, this is something from the Rogers group where they wanted to know what these internal lines look like. I tend to feel that sometimes these are Kit Kats, but yeah, not sure. So yeah, pretty small for a Kit Kat, not very satisfying. But this also demonstrates if the length scale here, I think that's 50 microns? Yeah, 50 microns. So you can make some fairly big trenches, okay, in your materials. Some other examples, controlled etching and deposition. So everyone that's got a FIB is always going to put their, their center name, the university logo. But you can do a lot of other fun stuff too. So we have dot arrays that can be used as like either masks or emitters. This is, I don't remember who did this per se, but it's platinum flower that they built. Now, you can do a lot of other cool stuff too. And the FIB can be used for sort of functional things and maybe not so functional things. So first example, functional, this was a platinum basket that was created to dip into a microfluidic stream and to pull out individual cells. All right, so this was the kind of test that they were doing where they had styrene spheres in a microfluidic stream, dip that in, okay, grab them and take it out. So these are, FIB's really good for designing kind of one-off structures to see, well, what can we do? Now, the FIB can also be used for things that are a little different. So this is the not-so-functional 1 billion scale Starship Enterprise, which I guess they didn't really do a very good job with this part here. A little bit damaged the system. But anyway, you can do a lot of really cool stuff. All right? If you've seen some of the news recently, MIT's got a really nice program where they do kind of FIB sculptures. They make like sand castles. And so it's pretty neat. Check it out. Okay, now the last major thing that a FIB is designed to do is make TEM samples. And you're going to hear a lot more about that in one of the next sessions. And I'm going to bring you through kind of the major steps that you need to make a TEM sample. So the first one is locate something that you're interested in making a TEM sample out of. We put down a platinum protection layer on that spot that we're interested in. Okay, then we're going to mill out the outsides around that protection layer, thin it down a little bit. Okay, this is the electron beam view, so we now have kind of a thin like wedge sitting in here. Okay, then we're going to bring in a needle. Okay, we're going to weld it using the platinum to that wedge. We're going to make some relief cuts in here. Okay, we're going to slice this out. Go. Very good. And then we lift out this small part. Okay, weld it to a grid. And then we thin it down so we can see all the internal structure. And you'll see why this is really important during the TEM talk. But this lets you basically take out very small portions of your sample, okay, and investigate the, the interfaces, between individual layers, and do a lot of really cool stuff that Vasek and CQ will tell you about in the next section. Some other really cool stuff you can do, serial slicing and 3D reconstruction. So you can take the FIB, you can slice out individual parts of this and then reconstruct all the data to show you things like the pore sizes in the shale structure. You can also use this to do things like elemental reconstruction or say channeling contrast reconstruction, or more appropriately like EBSD reconstruction if you want to know say the crystallographic orientation of your structure in a three-dimensional way. So FIBs are capable of doing that. We have some limited capabilities on this, but if you're interested, please talk to us. So we have two FIBs in the center. First one is our FEI DB235, has 7 nanometer resolution at 30 kV, has pretty good beam currents, has an Omniprobe for TEM liftout, has a Zyvex multiprobe station for doing in situ electrical characterization, has 3 GIS sources. So we have a platinum source, we have a carbon source, and we have a selective carbon mill. So if you have things like you want to cut through heavy plastics, or other carbon-containing structures like diamond graphite, that's what you would use this selective carbon milling for. Our other system is a Helio 600i. This is not ours, it's a stock image. If you've seen on the tours, ours is a little torn apart right now. But it has a little bit better resolution, 30 kV on the ion beam. Very high currents are obtainable. The major advantage here is that we have some advanced milling patterning capabilities which aren't available on our 235. Also has a charge neutralizer. Omniprobe for TEM liftout, so that's its major use. Has a platinum GIS, and it also has a retractable stem and BSE detector all inside the system. So to wrap this up, FIB pros and cons. The FIB is really good for patterning small areas, okay? One-off fabrication for functional devices, cross-sections, and precision TEM samples. What the FIB is not good for is it's not going to replace your E-beam or optical lithography, all right, because those things will do large areas. The FIB is not designed for that. Okay, and it will also not make hundreds of micron-sized TEM samples. So occasionally I get that request, make me a 500 micron TEM sample, and I go, no. You can try that, have a good time. So if you want small, locally precise, that's what a FIB is good for. Think of it like a scalpel, and that's what it will do for you. So with that, I'd like to thank our sponsors very much, letting us put on this wonderful AMC. And at that point, I will wrap up, and thank you very much for your attention.